Um, Cloudera is well known to be the first commercial Hadoop distribution. We've invested heavily in enabling big data applications on Hadoop, and we've been around for 5-6 years. Now, interestingly enough, Cloudera's name is a bit of a misnomer because we didn't originally when our founders started the company, this was in 2009 or whatever, they planned to basically build a data service on the cloud. 2009, apparently, it was a bit too early to do that, so we ended up doing a lot of on-premise work, but recently we've been spending a lot of our time investing in how to make Hadoop run effectively in cloud environments. So what I'm actually going to talk to you about today is some of the learnings and experiences we've had working with customers at fairly large scales, getting them to successfully run in a cloud environment, specifically AWS. We've got quite a few large customers who run multi-petabyte data sets, and they do processing of multi-petabyte data sets on AWS. And I want to talk a little bit about the challenges and design patterns that are most prevalent there. And I'm going to start with a little bit of a sort of basic intro to big data in the cloud. Forgive me if this is too simplistic, but I'll jump into a lot more detail shortly thereafter. One thing I want to make sure we all level set on is basic definitions of what we're talking about when we talk about cloud and big data. This one is pretty brain dead obvious to you guys, I'm sure. The cloud is the practice of using a network of remote servers hosted on the internet to store, manage, and process your data rather than using local servers. Again, pretty brain dead obvious to you guys. The key things here are it's remote stuff stored on the internet. What the cloud implies for your architecture, from our perspective, we look at it as 3 major tranches of changes. And I'm going to tie this back at the end to how this impacts big data specifically. Self-service, being significantly more automated relative to your traditional enterprise data centers. Very API-driven model, computers intermediate all your resource allocation, as well as interactions. This is going to be important when we talk about big data specifically. Vertical integration, you can consume the cloud at various levels of the stack. You can rent servers. You can get a big data service. You can get much higher level applications. Apparently, you can do BI out of the cloud starting yesterday. And you can, as a user, you get to choose which level works best for you. And from a multi-tenancy perspective, of course, multiple organizations are sharing this one environment, and there's an aggregation across all your resources, which has important implications for how things are set up. Now, big data, on the other hand, is typically thought of as this data of very large size, typically to the extent that its manipulation and management present significant logistical challenges. I actually disagree with this definition. There's actually a better definition that I think makes more sense. Size is actually only a relatively small aspect of what it means to be big data. Like big data to us is what happens when the cost of storing information becomes less than the cost of making the decision to throw away. None of the big data stuff that you see, like, it's not like data is increased in some foundational way. We have better ways of measuring things. We have better ways of capturing information. But really, the fundamental thing that's changed is the cost dynamics, where systems like Hadoop have made the cost of storing your information way lower. This is really a financial thing. This is not about some change in the way you do business. It's just that where before you would just throw away all this data that used to exist before, now you're like, hey, I can actually afford to keep this around because even if the value of data has changed, the value of the data is the same. I can afford to do this, and I can afford to extract that value out even if it's lower than you'd expect. So the traditional sort of data warehouse architectures are, I know exactly what this data represents. I know exactly what value it represents, and I'm going to store just that piece of information. Now you can actually store arbitrarily larger quantities of data with which you can actually extract much lower amounts of value potentially. That, to me, is really what big data is about. It's about lowering the cost of storing your data. So when I think about big data, I'm actually thinking about it as a financial transaction. It's about what value you can get out of your data. So when you start thinking about it as a financial transaction, you have to think about it as an asset, like just like you would on a balance sheet. Now, traditional enterprise would not associate any value in your CFO does not associate any value with data the way I think it should be done. They just tend to see it as, hey, there's a repository of data in there. You look at a warehouse, a physical warehouse, they're like, oh, that has some specific value associated with it. It's worth like $2 million or whatever. In reality, Your data warehouse is often worth way more than that because it represents a good chunk of what your enterprise represents. And that's never captured in a financial sheet. I think that's actually something which should change over time, but it is what it is. So when we start thinking about data, as a financial asset, you have to start thinking about it in terms of like financial metrics. The value of a byte is a fundamental measure here, which is like you apply some value function to say how it impacts your business, how it contributes to your business process, or how it contributes to other data sets that then generate value, how quickly you can get value out of these data sets. And the sophistication of analysis can generate different types of monetary results to your business. Of course, that's one side of the equation. The return on byte is tied to the cost of extracting that value. So the value divided by the cost to acquire, model, store, process. That's really the key measure that you care about is the return on byte. Okay. Now, so again, when I talk about big data in general, what I end up talking about is return on byte greater than 1 means it's worth keeping this data. Return on byte less than 1 is don't collect. Throw this out, put it on tape. Putting it on tape is basically throwing it out, except we pretend it's not, but whatever. Big data is fundamentally just lowering that water level on your iceberg. It's not changing anything in terms of what actually was there. This iceberg was always there. It's just that you can see more of it if you lower the cost. And one other important element when you think about this is time to value. So it's not just about what potential value there is. It's how quickly you can act on that. How long does it take from the time you acquire or generate a piece of data till it provides value? And this really does matter because you often can't extract value unless you do it in time. If you have a delay in shipment, you may often need to make an immediate action to fix that delay. That has a particular amount of value associated with it. On the other hand, understanding your delays over time can change your process in such a way that it has a different set of values associated with it. So my point being that fundamentally this all boils down to a cost structure equation. And when we talk about the cloud as well, it's really important to think about it in terms of the cost structure associated with this data set. Now, that's just a little bit of like level setting on what I'm talking about when I talk about big data. Now, I'm going to switch a little bit into more specifically Hadoop-oriented topics. Now, Hadoop came out of a system that was implemented in Google around 2000, and they actually wrote about it in 2004. They probably had it much longer than that. Once they wrote this like Hadoop paper, this MapReduce paper, which is a fairly seminal paper in the big data world, this guy called Doug Cuddy, who works at our company, implemented the original Hadoop implementation in open source around that time. Now, Hadoop was designed for a time when the data center architectures were fundamentally different. What I mean by this is that networks were much slower. So the concept of locality was really important when you have slow networks. So direct attached storage was like a big help to this. You actually have compute be moved to the storage because that reduces the time it takes to move data back and forth from the storage to the compute. This is it's not that radical if you think about it, but at the same time, it was an important concept when you're dealing with large data volumes is the idea that there is direct attached storage and that you move the compute to that data set. Typically in those data center environments, because it's not very cloudy, clusters tend to be fixed size. You create this one massive pool of your data and you run all your compute on that thing. And so you don't really share you don't share this data across clusters, and you have fixed size clusters. And typically all your users pointed to this one cluster. This is the standard sort of model for which Hadoop was originally created, which is like these, you have this file system, which is this one arbitrarily large file system. You have tons of computers which it represents, and you run your computer on those same computers. In recent years, and last, like, say, 10 years or so, there's been fairly foundational changes in the way data centers are designed, specifically things like SDNs, which are not heavily deployed in traditional enterprises, have been heavily deployed in cloud builders environments. AWS does not run a network that looks anything like your IT network at home. They have a very different setup, which allows them to give you like 10 gig connections from every computer to pretty much any other computer on their environment, including their object stores. So you're suddenly not finding that where before 12 local disks sitting on one computer could generate about 1.2 gigabytes, like about 100 megabytes per second is a reasonable approximation for what you can get, maybe 150 megabytes per second for what you can get from a single disk in terms of bandwidth. So 12 disks give you like 1 to 1.5 gigabytes per second, which is about a 10 gig Ethernet card. Suddenly, you can actually saturate the 10 gig Ethernet card from a remote storage and actually get the exact same performance. This is a big change. You could do that on a one computer basis before. You couldn't do that on a large scale because you always had an oversubscription policy to your network. You couldn't just like move petabytes of data across your network without having huge impacts on the network performance. On the other hand, with the way the data center designs are done with SDNs these days, you can actually do that. You can have 10 gig links between every single computer in your data center to all your storage. So remote storage is extremely important when you start talking about cloud, and because it gives you like a bunch of flexibility that you don't normally have. You can share data across multiple clusters. You put your data in something like an object store, S3, and that S3 object store can be the single source of data for 5 different clusters. Your QA, your test and dev, your UAT, your production, all of them can run off the exact same data copy, which is actually pretty interesting. It can be elastic now because your computer and storage are disaggregated. This is a really important thing because you can now scale your computer independent of your storage. The traditional Hadoop architecture just did not support that. You had your storage and your compute tied together very tightly. So you can do things in terms of scaling which are very different from what you could do before. And of course, because these clusters are so dynamic, you can actually create clusters as needed per app or per user. You can have an app which is defined as a particular ETL flow, and you can literally launch a cluster just for the duration of that app and shut it down. This is particularly common for certain class of apps that I'm going to talk about. So these are the fundamental architectural changes that have happened at the data center level. You could imagine doing this in an on-prem environment too, but most of the on-prem IT infrastructures do not look like this from a networking perspective. So the traditional architecture still makes a lot of sense there, but in the cloud, object storage fundamentally representing remote storage is a big transformation, and it's enabled by all these changes in data center design, which is somewhat invisible to us as users of S3. We just sort of like treat it as a magical black box, but this is sort of like the important thing that's going on here. Now, having said all this, I don't mean to imply that you can get the exact same performance as local disks with an object store. You do have performance degradation, but you're often willing to give up some of that performance degradation in exchange for the benefits I'm describing here. Okay? And by the way, feel free to interrupt me and ask questions if you have any at any time you have any. So now let me talk a little bit about architectural patterns when we talk about the cloud. Again, the big shift from our perspective is the fact that the object store becomes a really good place to store your data long term. Object stores have really nice price dynamics. Again, tying to the discussion we had earlier about the economics of data, object stores can, if you see the S3 prices, they're like usually around 5 cents a gigabyte, a terabyte, or sorry, it's a 5 cents a gigabyte is roughly what it comes down to, and like it's relatively cheap. It's usually cheaper than when you actually buy your own like HP gear or whatever. It's actually significantly reducing your price for maintaining this data. So if you assume that that becomes your core location for where you store your data, we tend to see things as like many classes of workloads that run on Hadoop. So the traditional type of workloads that Hadoop has been known for 5 years ago was very batch-oriented data processing. You're talking about doing ETL. You're doing maybe a modeling exercise where you're running a machine learning model. And machine learning models can crunch through large amounts of data and do a lot of compute. These kinds of applications tend to have a certain pattern, specifically ETL jobs. You don't run them arbitrarily all the time. You often run them in a schedule. Your data lands at a certain time. You pick up the data. You run your ETL window at night, perhaps, from midnight to 4 a.m. That's when you do your ETL job, and it's very consistent in pattern, typically. In those situations, there's a huge benefit from being able to do things like transient clusters. You spin up a cluster for the duration of your ETL job, and you spin it down. This is probably what most people are most familiar with in the cloud big data world, and it works really well. You can still use local storage if necessary because it can give you performance benefits, especially when you're doing transformations that require going back, writing back to disk and then picking it up again and doing more transformations. If you have a particularly complex pipeline, it's often better to copy data locally, do the transformation, and send the results back. But in other cases where you're doing simpler things, you may actually just never have local disk. You may just pull data from S3, do the transformation, and write back to S3. So that's one pattern of workloads. This is sort of the one that's probably the most well-known for Hadoop. And of course, you can now, when you're sitting in the cloud, you can actually take advantage of things like Elasticity. You can say, hey, today in my ETL window, I found that I have much larger amounts of data coming in because it's Thanksgiving, and you had like a lot more orders go through your system. Now you can actually do things like scale your cluster for that particular day's data needs. This is complex. It's not trivial, but it's possible to automate. So especially if you have some amount of predictability in spikes and whatnot, you can actually plan for that appropriately in your job itself. And these clusters tend to be transient. Again, one thing I found here is that a lot of people tend to start with transient clusters because it's very convenient. But as they do more and more work on Hadoop, their ETL starts becoming continuous. It's not usually like completely transient. So then you start having these longer running clusters. But then what you start doing is you start changing the size of the cluster over time. That's probably the most common pattern we see, which is like a few long running clusters that tend to do the processing. Your storage is in S3. And the cluster size varies dramatically over time based on the type of processing you need to do at any given point in time. So that's one model. The other model would be things like BI and analytics. You're running Tableau or what have you, ClickTech, or one of those kinds of tools, and you're exposing this data set that you have done all this ETL work on and prepped it and made it ready to be consumed. You're exposing this to your analysts. They're potentially exposing it to hundreds of users, thousands of users even. And these guys are going to come in with higher level tools. It could be a search interface. It could be a BI interface. And in this case, you don't tend to have the same flexibility you have in these ETL jobs where you don't have predictability of workload. Maybe you have some high level patterns. You can be like, hey, 9 a.m. to 5 p.m. is when like these guys seem to work, and that's when you have a lot more computational need. But after 5 p.m., everybody goes home, and it doesn't require nearly as many resources. So this gives you a different set of constraints to work with. And also, the other big constraint here is that your BI user is not going to be happy if they have latencies for their responses. So they're not super excited about like waiting for like 30 seconds instead of 5 seconds, which they could get with their traditional data warehouse environment. So when you start dealing with object stores, now it becomes a little bit more challenging, where ETL and modeling was just this slam dunk fit for running on object stores. It doesn't get that easy in the BI world because people do have a performance expectation, and they're not willing to give up that performance degradation that happens with running against remote storage. So in this case, it's much more common to have local data copies, which you can do even in AWS, and have your long-running cluster, which doesn't get shut down ever. You can potentially do some sizing things, but the sizing changes are much more coarse-grained. They're not as granular as you can do an ETL job. On an ETL job, you can literally change the size at the job level. Here, you're like, hey, maybe 9 to 5, I'll have a different size than 5 to 9 or whatever. So the level at which you can make sizing changes tends to be much more reduced. And in many cases, you may find that it's not even worth your while to do it. Again, it depends on the level of optimization you want to do there. But the other big thing here is that local storage often becomes required. Having said that, you may still want to have S3 as your persistent store for your data, but cache data as necessary in local storage in order to be effective. So slightly different pattern. And if you see sort of like the options that you have in the data warehousing world on the cloud, they tend to look like this in that they don't actually use S3 as their core storage. They have some connectors which make it easy to grab data. But they're all just doing the same thing that basically companies have done for like 30 years, which is copying data locally onto local disks and stuffing it in there. So while it seems very cloudy because of the architecture, it's not actually that cloudy because of this aspect of things. And that's for a very good reason. So I don't think there's anything wrong with this. I'm just pointing out that it's not as elastic as you'd ideally like it to be. You can't do this at a query level, and that's a fundamental issue. So I think the model is correct here, which is to do something like this. And then there are systems which are NoSQL systems. Why am I talking about NoSQL systems? In our world, we tend to look at all three of these classes of applications. So in our world, Hadoop specifically, we have a system called HBase. There are other options that look like this. Cassandra is another popular one. Mongo is another popular one. In this case, things are even more different because you're typically serving some live application off of your NoSQL store. And with your live applications, production requirements come in. You're potentially serving website requests, and responses have to be within 200 milliseconds, or end users face like massive delays. Your budget for how long you can take spikes is very, very low. And also, like when you're dealing with NoSQL stores, you have like a hash table, which is dispatching a particular object request to the right server. In these situations, like doing something like Elastic cluster has drastic implications on the code architecture because you have to repartition your data across nodes differently when you add nodes. You don't just add nodes and have it magically work. When you add nodes, you have to repartition the data so that the partition ranges change. This is a more drastic operation, and this is a more drastic operation in a more critical application because you're running a production web server potentially against this data set. So the level of granularity at which you're willing to do adjustments to your cluster sizes becomes even coarser, where I might do changes to my cluster size literally on a per job basis for ETL and modeling. I move to maybe once a day I can do some changes for my BI type things. And now with something like a NoSQL store, you're way more conservative typically. Some users can be a little bit more aggressive, but generally what we see is this becomes more like a capacity planning exercise than like a continuous elasticity exercise. So maybe like once a month you might revisit and think about what you might want to change. But it's not nearly as frequent, as dynamic as you'd see in the other two systems. And here, again, latency becomes critical, and you cannot get good latency from your object store. So it's much more typical to have local storage as the primary data repository. So while the other two models have often used the object store as your prime repository for your data, in systems like HBase, your local storage might actually be your prime repository, and your object store might be your backup location. It's where you save your data for safety reasons. That's a common model. Again, don't take any of these models as like a definite. You could almost always do other things here, but I'm just talking about the primary patterns we have seen so far in this world, which is these three classes of patterns. Any questions on any of this so far? Yes?
How do you keep the data in S3 and HDFS? You mentioned HDFS is a file system, and S3 also is storage. So what is the relationship between?
Yeah, so a good question. What is the relationship between HDFS, which is a distributed file system, and S3? So the funny thing is, Hadoop itself has this like massive misnomer because they combine two different things into this one name, which is the HDFS storage layer and the compute frameworks that are on top of it. So the right way to think about S3, so HDFS actually represents an API and an implementation. So there's an HDFS API which like your MapReduce, your Spark, whatever other big data system that you run depend on. Anybody could implement that API. And so S3 actually has an implementation of the HDFS API that you could just plug in. So you can actually use S3 as a direct replacement for HDFS in one way. You could use it in conjunction as well. But when I talk about like elastic workload where I run a job directly against S3, I'm effectively treating S3 as a replacement for HDFS, where you may not need any local HDFS at all. You may also find reasons, as I said earlier, that you may find reasons to have a copy of data in a local HDFS implementation, but that's a choice. That's not a requirement. So you can think of S3 as an alternative implementation of HDFS. That's the best way, I would say, to think about it. Does that answer your question? OK. Anything else on this front? OK. So I want to just talk briefly about transient versus long-running clusters. Transient clusters have some benefits. Specifically, when I talk about transient clusters, I'm talking about things where you will build an app that actually launches a cluster as part of the app. So one of the standard dichotomies between on-prem environments and cloud environments is that your apps can be much more self-contained in the cloud than they can in a more traditional environment. The reason for this is that if you have an app, you typically say, I've carved out a bunch of resources for this app, and this app assumes that this cluster exists and has in it some configuration which says, this is the cluster you're going to run on, that's what you should depend on. In the cloud world, with a more transient approach, the app actually creates the cluster that it's going to run on, and then like shuts it down at the end of the process. So it's a very different model. It's more of the DevOps model that people, they use the term DevOps a lot for this, but the fundamental idea is that your app is fully encapsulated, including the infrastructure it runs on. So an app, something starts the app up, like you could, in the ETL case, it could be as simple as like a cron job or a notification from S3. And that could literally trigger the entire process of creating a cluster, attaching like your job to the cluster, running the job, and then tearing down the cluster. So the app itself contains the logic for creating the cluster as necessary. So it's a much more fully self-contained environment. But this really doesn't work with if you depend on local storage, because local storage requires a cluster to exist where the data is sitting. So this fundamentally works best if you have remote storage as a prerequisite. Remote storage is a prerequisite for this environment. So it's one of the big benefits here are from a resource management perspective. Things is so much simpler. You don't have to worry about multiple users because your app runs on this cluster, and that's all the cluster is there to serve. And then it goes away. So you can do cost management really effectively as well. But long-running clusters often end up being much more cost-effective in many cases, where a lot of people start with these clusters which are ephemeral and these apps which are fully self-contained. They find that the cost dynamics don't work very well because they continuously have workload running, and the way the pricing is set up, it's often better to just keep your clusters up for a long period of time and just run your jobs within that cluster. They're sort of the average utilization and the peak utilization, and having your average utilization be always on just sort of makes sense, and just handle elasticity in the peak side. This requires a little bit more planning and forethought, but it can give you really good cost benefits. So as you find yourself scaling the number of use cases you deploy, this becomes a much more common approach. App can still be fully contained, and I'll talk about this a little bit more. You can still do this DevOps thing. It requires some changes to the way things work. But here you can also do things like local storage, which really doesn't work in the transient case. And one important use case I want to mention here, I talked about these different classes of workloads. Typically an ETL job or a modeling job is doing the work, is preparing the data in order to start doing things like BI on top of the data. So if you think that like you need the low latency response that requires local storage for your BI, your ETL job actually has to do processing from data that was landed in S3 and then dump it somewhere where the BI tools can access it, which is often HDFS. That's local storage. So one scenario that we see often is a long-running cluster with local storage attached to it, which has the data for BI, and that cluster expanding to just have compute-only nodes, which suck data from S3, do ETL, and then land it in this HDFS share that you have next to it. So you actually have these mixed mode patterns where you have the ETL jobs just running compute-only work, and these long-running HDFS clusters as well, side by side with these things. That's sort of the case where long-running clusters sort of make sense because you actually have this long-running cluster anyway for local HDFS. So that's particularly specific detail around how we see patterns emerging here. Now, I want to talk a little bit about the ability to do a DevOpsy model with long-running clusters. And I think if any of you have attended the Netflix talks before, they've actually done a really good job of this. They're one of the more advanced users of big data applications on top of Amazon, so they've done a lot of discovery in this space. And they have something like this. They have a system called Genie. There's other versions of this kind of thing that work in other environments. But fundamentally, if you want to do this DevOps model for long-running clusters, what often happens as a company which has a large amount of data processing happening in the cloud, you may often find that you have multiple clusters which are long-running. They are elastic, of course, in nature, but they're long-running. And they're all backed by some object store potentially. When an application wants to find the location to run, where before I described two models, one model which is hard-coded location of a particular cluster, and another model which is the app creates the cluster as necessary. There's actually a third model which is probably the right long-term model here, which is that the job says, I need a cluster with this many resources available to me. I just want somebody to give me that cluster back. And so there'll be often it's something that acts as a dispatcher. And this dispatcher can say, hey, this job needs this many resources. I have these 4 long-running clusters available. I'm going to pick the cluster that has the capacity to handle this person's resource needs. So there's effectively a layer of indirection here where there's a dispatch system which finds an appropriate cluster. This thing can get much more interesting here. While I talked about one set of policies, which is how much resources do you need, there are much more complex policies you can attach here. You could do things like this job wants to run in a very secure environment because it's running on secure data. in which case you need to find an environment where encryption is fully turned on. You need Kerberos to authenticate. You can find other types of policies. You can say, hey, this job is working on data that I know needs to be replicated across multiple regions. So I'm going to put it on this cluster, which actually has some policies associated with it that enables those kinds of things. So you can do much more complex dispatch rules by building a simple dispatcher. But even a basic dispatcher is very useful for handling multiple clusters in environment and finding an appropriate environment to run your job. So this is a little bit more advanced. I'd say some of the more cutting-edge deployments tend to do this, but I think it's still a ways to go before it becomes common parlance, at least. Unfortunately, there's no easy out-of-the-box system to do this, so you oftentimes have to build something custom for these kinds of situations. Okay. So I've talked a lot about current patterns. One thing I want to talk about is some of the things you can do in the cloud that are not possible on-prem, which are not yet being done in the Hadoop environments. There's a bunch of stuff you can do where, given that you're running in the cloud, you can actually make the systems much smarter. There are very few systems available today which can do completely smart scaling. You can imagine, like in a Hadoop cluster, that you can shrink and grow based on data set sizes. I talked about that. There are actually many more metrics you can leverage. We've done this in some customer POCs where you have a Spark job, it's doing a machine learning model based on various attributes of CPU usage, for example. It's getting bottlenecked on CPU. You can actually create a policy that spins up more compute to run against this thing. So you can imagine much smarter policies where the job will auto-scale itself. What you really want to get to at some long-term position is forget the number of nodes involved. You have a job. It needs to do some processing on some data. And the cluster sizes itself correctly to run the job in the right amount of time. Frankly speaking, this is still a pipe dream because the complexity of a lot of these applications is such that it's very hard to predict what is going to be needed to run successfully. But I think there are ways in which we can approach this problem. Again, this is a little future-looking. This is not stuff that exists today in any practical sense. There are like attempts to do this which on a custom per-app basis, but not in a generalizable way. But I think this is sort of like where Hadoop will go when in the cloud. Other things you can do here, there's a lot of elements in Hadoop which are necessary for high availability. What you don't want to have happen is you have a 16-hour ETL process, and R15, your master node fails, and you have to restart your job. Hadoop is actually pretty resilient to these situations, but we can do much better. We have high availability today where you have two masters, and you can fail over to the right thing. But when a failover happens, somebody has to come in and actually like fix the failed node or create a new node and set this up for HA again. In the cloud, you can actually do much more dynamic things where you can just automatically create a new master and just auto-provision the stuff and get it attached. So the amount of IT operation touch which you need can be significantly reduced. Again, unfortunately, this is not done yet, but these are the kinds of things I think are really important going forward for Hadoop to address as we get better running in the cloud. Again, we talked about smart job dispatch, which is what I was talking about earlier. That's not a standardized component of the Hadoop stack today. I think it's important to create something which is a standard way to do those kinds of policy-based dispatching. There are people who do this with tools like Uzi, which is a workflow manager in Hadoop, but it's sort of very custom on a per customer basis, and I feel like this needs to be generalized much better. And even doing things like Yarn, which is a resource manager, decides where jobs run. If I want to do my ETL job in the same cluster where I store my BI workloads, you may often want to partition your job so that some nodes run your ETL work and some nodes run your BI work so they don't step all over each other. That's another case where we can actually do some interesting work in the resource manager to make this much more dynamic and intelligent. So just wanted to give you a taste of the kinds of things that we can enable going forward, but Hadoop doesn't do yet. It's one of those things which needs to improve. Anyways, that's I'll leave that there. And I want to switch briefly to some interesting things that are happening at the chipset level that actually impacts big data quite dramatically. So like Intel has been doing a bunch of work in actually enabling data applications to run much better, with much better performance by doing innovations at the silicon level. For those of you who are doing encryption type work in Hadoop. And this is very common, actually. Many of our secure customers want their data to be encrypted at all times. You can see S3 and EBS have both added encryption capabilities. We've seen pretty dramatic improvements by actually taking advantage of chipset features, and most of this should be hopefully transparent to you guys because the software vendors just do the right thing here. But what we've found is that when we take advantage of things like encryption on chip, the cost of encryption drops from nearly 30% CPU cost for software encryption to like 3 to 5% when done at the hardware level. That's one example. The even more impactful example in my mind is the AVX 2.0 instruction set. That's something that's been out in the last couple of years in their chips. It's pretty dramatic. We have a customer who's running very large alternating least squares, which is a recommendation system, machine learning algorithm. 60 million users, 10 million items, 100 million ratings. The training time improved decently. They improved by 30%, so you can actually see that the time it takes to train models on really large data sets improved. The prediction time to do your scoring went up like 200 times. So it's actually, this is an approximation, it's actually more than that. But one thing that you should keep in mind when you start thinking about instance selection in the cloud, for example, is whether or not the instances that you're running actually have these kinds of capabilities. If you're doing large ETL or especially machine learning work specifically, this has huge impact. And I actually have a table here of specific instance types that actually do have some of these capabilities in them. So I think a lot of these instances are pretty well. General purpose M4s are actually very heavily used for our workloads. The D series is also very heavily used. So for Hadoop on AWS specifically, I often recommend the D series if you want local HDFS. So the BI class workloads tend to be heavily run on D series. Same is true for HBase class or NoSQL stores. The D series is a very good choice. But for your more dynamic workloads, the M series is a good choice as well. Again, depending on the specific type of computation you're doing, if you're more compute heavy, you may want to look at the C series and so on. But the two that we tend to see the most are the D and M series, and they both have some of these capabilities I was talking about as well. Okay, so that's a super quick look at things that are happening with respect to big data on the cloud. I'm going to end quickly here and talk just briefly about how this stuff all comes together. So when you're running in the cloud, fundamentally, computers intermediate all our interactions. This is going back to the original 3 things that I put up on the slides. Everything that can be measured will be measured. Systems like S3 dramatically reduce the cost of storing this data, so it's much, much more cost efficient to actually store lots of data that you would throw away normally. Consumerization is a massive trend which really matters a lot in new application development. Employees, customers, everybody expects more personal and customized interactions, and you can only do this by understanding each interaction in its specific context. Experimentation. If you have large amounts of data and you make it available to your data analysts, you can actually have people try lots of different things to see what they can get out of this data set. Again, cost is a big driver of a lot of this stuff. And then wrapping up here, from where I started earlier with cloud, this is how like all those 3 trends I mentioned relate to big data specifically. With self-service, there's a lot more data exhaust that's coming out when you're dealing with applications in the cloud where computers handle every interaction. Vertical integration means that analytics will become much more pervasive. As you can do more and more of these kinds of things, like there are more systems coming out which are not just talking about individual ETL, database, BI type tools, but they're trying to combine these things into their actual applications. And again, aggregating the data from many users means storing tons of data, which yields new opportunities and techniques for analysis. That's basically where I was going to stop. I'm going to open it up for questions now. Any questions at all?